All right, so let's work this problem. We want to draw the shear force and bending moment diagram for this problem. A couple of things you want to notice right off is we have a pin connection at A, and at C this is fixed. So you should be able to notice that if I try to draw a free body diagram of the whole structure, I cannot get the reactions. So I'm going to break it apart here at B, which is a hinge, and I know my moment there is 0. So the first thing I want to do is do the statics of the two pieces and then draw the resulting shear force and bending moment diagrams. So let's see if I can make two columns here. So I'll draw first A to B, and I'll assume at the roller I have a positive shear at A, and at B I'll have a positive shear at B. Now technically at A I would have a axial force, but you'll probably see that that's going to end up being 0. I have my distributed load. Let me draw that in. It's triangular shaped. And to do my statics, I'm going to take the concentrated equivalent of that. So that would be the area of the curve. So 150 times 6 divided by 2, what is that, 450 pounds? Is that right? And whichever distance you want to choose, I'll choose about B. So that will be 2/3 of the distance. 2/3 of 6 is 4 feet. Okay? Now before I go solve all that, I'm going to go ahead and draw the piece on the other side. So if I assume these directions, then I know that my shear at B is this direction and that axial force is in this direction. And now I'm going to assume things at C. So at C I'm going to assume positive shear at C, positive bending moment at C, and positive axial force at C. I also have a triangular load. The concentrated equivalent of that will be, what is that going to be? I don't know what's half of 450. 225. 225 pounds. And from the cut, from this moment, from this area, it'd be 1/3 the distance. That's 1 foot. So there's my pieces, and I can do my statics. Let me just name, I'll just call this free body 1, free body 2, and I'll come over on this side and do the statics. So for free body 1, I can sum moments about B. I'll use right-hand rule for my moments, and I'll sum moments about point B. And when I do that, I'll have the moment due to the 450-pound force with a moment arm of 4 feet, and then my shear force creates negative moment with a moment arm of 6 feet. So it looks like the shear at A is equal to, oh, I'm kind of running off the top there, sorry. So what is that? What's 2/3 of that? 300? Is that 300 pounds? Can you guys calculate that for me real quick?
Yes, 300.
300? And then I can sum forces in the y direction. And I have my shear force at A acting up, my shear force at B acting down, and the 450-pound force acting down. So therefore, the shear at B is equal to negative 150. So since I found the shear at B here, I have the shear at B here. And I can move over and find these things. So from free body 2, I need to find the shear in the moment. So I'll do the same thing. I'll sum moments about, bless you, about C. So what do I have? Well, I have the moment at C that I'm looking for. Positive moment created by the 225-pound force with a moment arm of 1 foot. And then I have the shear at B. Now the way I've drawn it here, this is creating negative moment. Remember, B is negative. Really? So that means it's actually down, which means it's creating positive. Oh, I forgot the dimensions here. This was 3 feet, and this was 6 feet. Times 3. So I've got the moment, plus this, and plus this. So what's the moment at C? Negative 675, and that will be pound feet. Negative, huh? That sounds reasonable. So the last thing I need would be my shear at C. I think I can squeeze that in over here. So I'll sum forces in the Y direction. According to this free body, I have B acting up, C acting down, and my 225-pound force acting down. So the shear at C should be what? Well, I found the shear at B as negative 150, so I got negative 150 plus 225, right? 375? Yeah.
Why is your number about C and CB? It should be negative, shouldn't it? Because it's going counterclockwise. Sorry.
What are you talking about?
Your VB times 3.
VB times 3? Well, VB is negative. So it's. I didn't change my sign. I just know that it's going down. That would create positive moment. That's why it's positive here. The other way to look at it would be this creates negative moment, but VB is negative. A negative times a negative is a positive. So what am I got? Okay, so I got shear up, this shear down, this load down, but I know this is negative, so it looks like it's negative 375. All right, so I have all my pieces now. So let's go back over here, and I'll extend my template and establish the X direction, positive shear. All my values will be in pounds. And let's apply our technique to draw the shear diagram. So what do I know about the shear? I know the shear at A, it was 300, right? And do I know the shear at B? What's the shear at B? Negative 150. Now, can I make it work? Let's see. I'll have to draw this over here, but we know that the change in shear is the area under the load diagram. Right? So the change in shear over this 6 feet needs to be the area under the load diagram, which we know is 450. It's acting down, so that's negative. So 300 minus 450 is 150, so that works. We also know that the slope of the shear diagram is equal to the load. Right? So that means at this point the load is negative, and it's large, and it goes to 0. So that means we have a 0 slope here and a negative slope here. And if you kind of connect those, you get something like that.
Why is it 0?
Why is what 0?
Why is the slope?
Well, remember the slope is given by the load, right? So you look up here, what's the value of the load right here? Well, it's 150 and it's negative. So that means this slope here is actually negative 150. And it decreases to 0. Okay? Now that gives us a new point to be concerned about, this 0 point. I'll just call that some distance x1. Now you can see where we're going to have some difficulty drawing the moment diagram. And why will that be?
There's supposed to be a maximum or minimum that 0 is excellent for?
That's true, but trying to find the area under this part of the curve is going to be a little tricky. I mean, you can write the equation and integrate it, but just looking at this as a geometric shape, I don't know what that is. Now, this piece over here, I do know. This is a parabolic section because I have a 0 slope here. But over here, I don't have that. So it's going to be a little tricky trying to figure out that area on the fly. So you can see that our technique can run into some trouble when you have triangular loads. It can be a little tricky. Let's just see what we can do. Let's see if we can figure out, can we figure out x1? Well, if I expand that up to here, remember that the change in shear, which we know, it's going to go from 300 to 0. So that means our change in shear is minus 300. And what's the area under the load diagram in the same position? Well, now it gets really tricky. What's the area under this general trapezoid of length x1? You're going to have to write this as a function of x1, and then it's going to be a mess. And your equation here will be quadratic. You'll get 2 answers. So this is kind of a problem that you don't want to see. I mean, we can work it, but in context of what we're doing in class, you can see we've got big problems. Everybody see what I'm talking about? This is a problem where, it's an oops problem, right? It looks very simple, but you can see our basic strategy kind of comes to a halt, and it becomes a very difficult application. And I bet you'll find out the same thing over here. But let's try it and see what happens. So if I extend my components here, yeah.
Why did you change in shear negative 300?
Because I'm starting at positive 300 and going to 0. So that'd have to be a negative change. So let's see what this one looks like. So this will be a much smaller diagram. So what's the shear at B? It was negative 150, right? And what's the shear at C? So we're going to start at negative 150, and we should end up at negative 375. Now, does that work? Well, the change in shear is the area of the load diagram. What's the area of the load diagram? 225 negative. So if you take 225 and you add to one, or subtract it from 150, you do get that. So that's good. What about the slope? Well, it starts off with, it's given by the load. The load starts off at 0 and becomes a larger negative value. So you get a shape that looks like this. Now, believe it or not, this is an easier one to find the area under the curve. If you look at it carefully, you'll see that this is a rectangular piece. And what's this? This is called a spandrel. It's the other side of a parabolic curve. So this, the area for this is not hard to find. It's 1/3 base times height. So I can find that one. We can draw the moment diagram for that one pretty easily. So let's do that. So drawing the moment diagram. So what is the moment at B? Don't forget where we started. What's the moment at B? Should be 0. What's the moment at C?
0.
No. Negative 675. How do we make those things meet? Well, hopefully I'll get a change in my moment. Should be the area under the shear diagram. So let's look at what that would be. So what's this rectangular piece? It's 150 times 3. That's negative 450, right? So let me just kind of pencil in that area is negative 450. And what's this area? It's 1/3 base times height. Well, 1/3 of 3 is 1, and the height here is 225. So that's negative 225. You add those together, you get negative 675, so it matches. So the area under the curve is the change. And what's the slope? The slope of your moment diagram is the shear. So it looks like you start off at a negative shear, right? And it gets larger. So it would look maybe something like that. And that's your moment diagram. Not so easy on this side, as you see. So I hate to say it, but I'm going to bail on that one. I just wanted you to see that sometimes, it can work out okay. We're using our information we have about our geometry, and other times it can be very challenging. And we could solve this problem, but I don't really think it's good use of our time moving towards the test. I think we should probably work ones that are more likely that you would see on the exam. So I guess with that said, I'll stop this.